Okay. Just because of the nature of the subject, I think it is worth giving a couple more examples of what you might see in your homework, for instance, or in a test. What if you are asked this? Let's sketch a possible graph with the following criteria. Sketch a possible graph of a function f that is satisfying the following. First of all, f of 0 is equal to 0, f of 2 is equal to 3, f of 4 is equal to 6, and f prime of 0 is equal to f prime of 4, which is equal to 0. Okay? Second criteria, f prime of x is greater than 0 for x in between 0 and 4. And f prime of x is less than 0 for x greater than 0 and for x greater than 4. Excuse me, it's for x less than 0 and for x greater than 4. Okay, so I have some information about the function and the derivative. What about some information about the second derivative? F prime prime of x is greater than 0 for x less than 2, and f prime prime of x is less than 0 for x greater than 2. Give you a minute to write that down. We're going to use all that information. Okay, and it all looks a little bit confusing here. So let's see. Maybe I want to make a little number line like we were doing beforehand with all this information on it. I'm told a few things about x equals 0, x equals 2, and x equals 4. So I'm going to put those three numbers on this number line. Okay? And I'm given information about the function itself. Maybe I will do that in green, the function f. And I'm given information about the first derivative. And I'll do that in red, f prime. And I'm given information about the second derivative, f prime prime. Okay? What do I know about f? Well, f is 0 at 0. F is 3 at x equals 2. And f is 6 at x equals 4. And actually, well, no, that's okay. All right. Second derivative. What do I know about the second derivative? Well, I know that at 0, the second derivative is 0. At 4, the second derivative is 0. I know that for x in between 0 and 4, the first derivative is positive. I know that for x less than 0 and greater than the 4, second derivative is negative, or first derivative, excuse me. So graph is going down here, graph is going up here, and graph is going down here. Okay, so there's first derivative. Lastly, information about the second derivative. I'm told that the second derivative is positive for x less than 2. Second derivative is positive. So graph is concave up here. concave up here. And then for x greater than 2, second derivative is negative. So the graph is concave down there. Okay. Now, I'm going to separate those. All right, I'm going to label a couple things. First of all, if the first derivative is 0 at a point, that's a critical point. That's a critical point. Let's see, what do I know about that? I know that I can tell here that where the first derivative is 0, in this interval here, the second derivative is negative. So this point will be the location of a relative maximum. And then very similarly, critical point is where first derivative is equal to 0 here, and the second derivative is positive. So this will be a location where the function is at a relative minimum. Okay, let's see here. I could probably draw a graph with that much information. Okay, so this is 0. This is 2, 1, 2, 3, 4. I'm told a little bit about the y values here. F values are the y values. I'm told that y value is 0 at 0. So I have a point, 0, 0. I'm told that the y value is 3 at x equals 2. So I have a point here, 2, 3. Oh, I'm out of room, aren't I? Let me rescale the axes here. Let's make this 2, 4, and 6. There we go. So a point at 2, 3, which is about there. And I have a point at 4, 6, which is right there. Okay. This point is the location of a relative minimum. This point is the location of a relative maximum. What about 2? Well, it looks to me like the graph is concave up here, and then at some point it changes to being concave down. So this point 2 looks like it's a inflection point. This is an inflection point, a place where the concavity changes. Okay, so that's enough to where I could draw a little bit of a sketch. I know first derivative is 0 there, so the slope of the tangent line has to be horizontal. I know the graph has to be going down to the left here, and then it has to turn and go back up as told by my first derivative. Okay, I know it's going to be concave up, and then at some point turn and go concave down. At that point x equals 2, and then the graph will decrease after that. Okay. Let's see if it fulfills all of the criteria here. Okay, first, we already discussed the function values. First derivative, graph is going down until it hits 0 here, up from left to right until it hits 4. So that's here. And then it starts going down forever. So that's good. The graph is concave up from, it looks like negative infinity to 2. concave up until it's here, and then it turns and becomes concave down after that. And it's like that forever. That graph looks like it fulfills those conditions. I highly recommend on these that you draw a number line just to organize your information. It helps to draw a graph. This is not the only graph that could be drawn because I don't know absolutely everything about this graph, but this is one possibility for sure. Okay, one more, and then we'll be done with this section. Let's say we're given the curve y is equal to x to the fourth minus 4x cubed. And let's discuss this. Let's discuss the following. Concavity, points of inflection, and local max and min. Local max and min. All right. So let's do this. If I want to find anything out about concavity or points of inflection, I need the second derivative. If I want to find local max or min, I need the first derivative. So a good plan of action would be to find those. Let's find f prime of x. The above is a polynomial, excuse me. Let's use the Leibniz notation since I'm given the function in terms of y. dy dx is equal to derivative of x to the fourth, which is 4x cubed minus 4 times 3, which is 12, times x squared. The second derivative, d squared y dx squared is equal to the derivative of dy dx, which is equal to 12x squared minus 12 times 2, which is 24x. Okay, so I have the derivatives. Let's find any critical points. Find any critical points. So this is where f prime of x is equal to 0, or f prime of x does not exist. So first derivative, 4x cubed minus 12x squared. I'm going to set that equal to 0, factor, and solve. Factor out a 4x squared times x minus 3 is equal to 0. This gives me 4x squared is equal to 0, or x minus 3 is equal to 0. Excuse me, 3, not 13. So this left-hand equation gives me that x is equal to 0. Or if I add 3 on the right-hand side, I get that x is equal to 3. So there are 2 critical points. Anywhere the derivative does not exist. Well, the first derivative is a polynomial. There are no such locations. Okay. So I have those. While I am at it, I might as well find possible inflection points. Possible inflection points. These are locations where the second derivative is equal to 0, or the second derivative does not exist. Okay? So the second derivative we said is 12x squared minus 24x. I'm going to set that equal to 0 and solve. I'll factor out a 12x times x minus 2 is equal to 0. This gives me that 12x is equal to 0, or x minus 2. Excuse me, x minus 2 is equal to 0. On the left-hand side, I get that x is equal to 0. On the right-hand side, I add 2 to both sides, and I get that x is equal to 2. So 2 possible inflection points. I also should check points where this is where that second derivative is equal to 0. Points where that second derivative does not exist. Well, again, second derivative is a polynomial. It is right here. It exists everywhere. So there are no such values. So I have 2 critical points, 2 possible points of inflection. Let's put these on a number line. And I am actually going to put both my critical points and my points of inflection on there so I can discuss concavity. My critical points are 0 and 3. My possible inflection points are 0 and 2. Okay, so I have those. I want to figure out things about the first derivative, f prime, and the second derivative, f prime prime. Okay, so let's see here. Maybe let's use the second derivative test first to give me a little bit of information about the critical numbers. F prime prime of 0, one of the critical numbers, is equal to 12 times 0 squared minus 24 times 0, which is equal to 0. So the second derivative is 0 here. F prime prime of 3 is equal to 12 times 3 squared minus 24 times 3. All that I really care about is that second derivative, or that value, is positive. If you put this into your calculator, you're going to get a positive number. So the second derivative is positive there. All right. Well, what's that tell me? I know something about this right-hand one. I know that the graph is concave up at that critical point. So this classifies this as a local minimum. Okay. What about this left-hand one? Eesh, I don't, that's the case where the second derivative test failed. I should probably note that. The second derivative test failed. Derivative test fails here. I got 0, not a positive or negative number, so I have to fall back on my first derivative test in order to classify it. So I'm going to test values. Let's test something to the left of 0, maybe -1, something to the right of 0, maybe 2, in the first derivative. So f prime of -1 is equal to, I factored this earlier. I'm going to use the factored form. 4 times -1 squared times -1 minus 3. This gives me something positive times something negative. That's negative. So the first derivative is negative here in this interval to the left of 0, because that's where -1 exists. I use 2, or actually let's use 1 here instead of 2. I believe that would be easier. F prime of 1 is equal to 4 times 1 squared times 1 minus 3. Well, that gives me a positive number times a negative number that is also negative. So it looks like in this interval, to the right of 0, the graph is also negative. Well, if that's the case, this is actually not a max or a min. Not a max or a min. First derivative test didn't work, second derivative test didn't work. If both of those tests fail, this is not a max or a min. Okay. So there's those. Last thing I probably want to do is, okay, there are 2 locations where the concavity can change. I know here, the concavity can change here, and the concavity can change here. I know what the concavity is here. I need to figure out what it is here and here. Only possible way that I can do that is to choose test values. So maybe let's test -1 in the second derivative. F prime prime of -1 is equal to, I'm going to use the factored form, 12 times -1 times -1 minus 2, which is something negative times something negative. This gives me a positive number. So the second derivative is positive here, which means it's concave up. And similarly, f prime prime of something in this interval from 0 to 2, excuse me, maybe let's choose 1, is equal to 12 times 1 times 1 minus 2. This is a positive number times a negative number. Together, those give me a negative number. So the graph is negative, or the second derivative is negative there, which means the graph is concave down. Okay, so that tells me that at this location 0, the possible place where the concavity could change, the concavity does change. It goes from concave up to concave down. So this is an inflection point. And similarly to this possible location where the concavity could change, at that place, the graph goes from concave down to concave up. So this is also a point of inflection. Okay. Well, let's see. What could we say here? This is the interval from negative infinity to 0. This is the interval from 0 to 2. This is the interval from 2 to 3. This is the interval from 3 to infinity. What are things that I could say from this? I could say, first of all, relative extreme values. Some notes about this. I know that there is a relative minimum, not mint, relative minimum at x equals 3. That's something I could definitely say by the second derivative test. I could say that the graph is increasing Well, where is it increasing? Did I find any locations where the first derivative is positive? Doesn't look like it, but I didn't really test here. But let's look at what we did down here. Remember that at a relative maximum, or minimum, excuse me, such as this, the first derivative is negative to the left of it, and it is positive to the right of it. So without even testing values in this interval here, I could say that the first derivative is actually positive here. I know that it's negative here because the only places the first derivative can change sign are 0 and 3. And I know by the fact that this is a relative minimum that it's positive here. So the graph is increasing from 3 to infinity. It is decreasing on all of the other intervals. Negative infinity to 0, 0 to 2, and 2 to 3. The graph is concave up from negative infinity to 0, and from, where is it, 2 to infinity. It does not change concavity at this critical point. It can only change at the locations where the second derivative is equal to 0. And the graph is concave down on 0 to 2. Lastly, I could say that there are two inflection points. At x equals 0 and x equals 2. All right. So that is a good summary of what that derivative can tell us. And I recommend that you go graph this function just to see if all these features line up and to see how it works. I think we'll be done for this section. I'll see you guys next time.